Alrighty, y'all, are you ready to learn? Today we're taking a look at the recitation for April 1st. Right, and this one we're going to be looking at momentum and generally like the conservation of momentum. Right? So our first question, we have an astronaut. Right? There's our astronaut. And I'm going to say our space station's over here because our astronaut is currently floating away from our space station with a velocity of 0.5 meters per second. All right, and I'm just going to say away from the spaceship is our negative direction. So we just have to pick a negative, and that's what I've decided to do. And our mass of the astronaut, right, and their gear is given to be 200 kilograms. We'll call that M1, right? This is the first thing that's happening. That's our 200 kilograms, right? And we're drifting away, and now we have to try to use our jetpack to move back towards our spaceship. So our second state, after we've ejected our nitrogen, we are now moving towards the spaceship with positive 0.5 meters per second. I'm going to call that V2. Okay. And again, since I called this negative, I'm calling this positive because velocity is a vector. Right? But that's not the only thing that's happened. We had to have caused that change in direction somehow. So our puff of nitrogen gas, that's when it's going to have caused our thing. Right? And we have some M2 of the astronaut, right? And some Mn of the nitrogen. Right, again, we're trying to find our mass of the nitrogen. How much nitrogen? We do have the velocity of the nitrogen, right? Our Vn equals negative 100 meters per second. All right, we're given 100 meters per second. Again, it's negative because I said this direction was negative because, right, the nitrogen's going that way. So, right, we're trying to figure out our Mn. With our conservation of momentum, we know that whatever momentum exists in our system initially is the same momentum that's going to exist in the final state, right? We take a picture, figure out the momentum, and we take a picture after and figure out the momentum. And we can set them equal, right? Since momentum's a vector, we do have to keep track of these positives and negatives, right? Velocity is a vector, momentum's a vector. All right, so let's find our momentum of our initial state. We have some mass of the astronaut and their gear and some velocity. So it's going to be 200 times negative 0.5. Okay, and that's our first momentum. Now our second, it's a little bit more tricky, right? We have the astronaut moving to the left. We have our nitrogen moving to the right. Since we defined our entire system originally, right, our nitrogen was part of this gear. The nitrogen's coming from the astronaut. It's coming from the tank that's attached to the astronaut. So now our mass of the astronaut in the final state is not going to be this 200 kilograms because we're losing some mass of the nitrogen. So, right, we have our final momentum of the system is going to be the momentum of this astronaut without the nitrogen plus the momentum of the nitrogen without the astronaut. Right? So, right, M2 times our positive 0.5 plus our Mn, our mass of the nitrogen, times our negative 100. Right now, this looks like we have, like when we set these equal, it looks like we're going to have one equation, but two things that we don't know. But we know more about our mass of the astronaut, right? We said this was the mass of the original mass. Oop, I'm not zooming right. Our original mass without our nitrogen. So this M2 is just going to be 200 minus this Mn. If I can say that, right? Setting them equal, we're going to be 200 times negative 0.5 is negative 100, right? That's just coming from up here. I'm just simplifying it. Times, right, we said it was 200 minus Mn. It's our new mass of the astronaut. That times our 0.5. And that's going to be plus, actually I'm going to take this minus and just move it to the front, minus 100 Mn. Okay. So now we have one equation and one thing that we're solving for, and lo and behold, that's what the question's asking for. So solving for that mass of the nitrogen, right, it's just going to be a wonderful little simplification algebra problem, which I won't walk through for right now, but plugging everything in, we're going to get the mass of the nitrogen equals 1.990049751 kilograms. Now, this is a super small amount compared to our original 200 kilograms. It turns out, right, if I just assumed that the astronaut stayed at 200 kilograms here, the answer I would have gotten, right, was 2 kilograms. If I ignored the fact that the astronaut lost some mass here and just said it was 200 before and after, I would have gotten that the mass of the nitrogen is 2 kilograms, which is very, very similar to this. So you can assume that they're just not going to change in this case, but it is important to think about where the mass is coming from and how it's starting and where it's ending when we're thinking about momentum when we're defining these systems, right? Because our initial system we defined was the astronaut with all the gear, which included the nitrogen. All right, now we get to go to two-dimensional momentum, right? So we have a Mini Cooper driving west at 10 meters per second. 10 meters per second, I'm going to call that VC for velocity of the Cooper, and I'm going to call that VC1 because it's our before picture, right? Take a picture of before, and that's our thing, right? And our mass of our Cooper is Mini Cooper. I'm just going to call it a Cooper, but we have a mass and a velocity, right? So if we really needed to, which we will eventually, we can get our initial momentum of the Mini Cooper. And we also have a Toyota Camry, which I'm not going to abbreviate with a C as well. This one's going to be T. So our velocity of T initially was 15 meters per second. And our mass is, 2,000 kilograms. 2,000 kilograms. All right. So it's slightly more massive and going a little bit faster. Slightly less massive, going a little slower. And we know that the cars stick together after the collision, which means it's going to have some momentum, but our final mass is going to be mt plus mc. Right? So now we get to think about our total momentum before and after. So let's start with our total momentum before the collision. So let's see. Our momentum of our Mini Cooper initially is going to be our mass times our velocity of that Mini Cooper. Again, remembering that this is a vector and this is a vector, it's going to have a direction. So if we have our 12,000 times our 10, that's going to give us 12,000, because I'm remembering, and that's kilogram meters per second. That's our units for momentum. But right now, this is just a number, so we get to say that it's going west. Okay, because again, our velocity is going west, therefore our momentum is going to be going the same direction. Our momentum is given the direction of the velocity, but multiplied by mass, the scalar, to change the magnitude of our velocity vector into the magnitude of our momentum vector. Okay? So now we say that our momentum of the Toyota one is the same thing, our mass of that Toyota times our velocity. Again, these are still vectors, so we're going to say that it's 30,000, because that's 15 times 2,000, yeah, 30,000 makes sense, kilogram meters per second, and that's going north. Again, we just take the direction of our velocity vector there. So now it's super easy, right? We're just adding up like we did before. We just said our momentum of one thing plus the momentum of another, right? So we can just do 12,000 plus 30, but we can't because they're not going the same direction, right? Over here, we could just say positive and negative because they're both along the same axis, but that's not how we add vectors when they're going in different directions. We have one vector going west, one vector going north. Luckily, they're perpendicular to each other, so we can just Pythagorean theorem, but right, our magnitude of our total initial momentum, right, remember the absolute value sign doesn't mean absolute value, it means magnitude of a vector. We can take the square root of our 30,000 squared plus 12,000 squared. All right, and that's going to give us 32310.98884 kilograms meters per second. Okay, roughly that is our magnitude of our momentum. But again, our answer, it's asking for our total momentum. This is not our answer just yet. This is the magnitude of our momentum vector, but we still need a direction. All right, so when it asks, will our answer be one value or two? There are multiple ways to report a vector. Right? We can say an x component and a y component. Again, but that'll still be two answers, an x and a y component. Or we can say a magnitude and a direction, and it'll still be two values, but just in different contexts, right? So our theta, right, it's going to be inverse tangent of opposite over adjacent, so that's going to be 30,000 over 12,000. Right, and if you need more practice setting up these vectors and equations, you can go back to some of the older videos, or you can ask for more help from the physics clinic. Again, because this is just, that says negative t, that should say -1. Right, inverse tangent. And that's going to give us an angle of 68.1985951 degrees. And that angle is going to be measured from, I said, opposite, adjacent. That's going to be north of west. So we have this magnitude going west, and here's our 68 degrees, or 68.2 degrees north of west. Cool. So that's our total momentum before the collision. So now what's our total momentum after the collision? We said before we take a picture before and we take a picture after, and the momentums are going to be the same. So magically, I can just take this. There's my answer for the momentum after the collision. I have a magnitude and I have a direction of that vector, and it's not going to change because our momentum is conserved. So now we get speed and direction of the cars after the collision. And remember what I was saying before, that, right, our speed, our direction of our speed, right, our velocity, dictates the direction of our momentum vector. Well, it's the same thing. If I know my momentum's going in a certain direction, I know that my velocity is also going to be going in that direction. So I can just take this and say, there's my direction that the cars are going after the collision. 68.2 degrees north of west. Now we just need the speed, just need the magnitude, right? And the fun part about this is the same way we set up our equations up here. Again, we're just doing the same thing but working backwards. So I'm going to steal this. But instead of looking at our momentum of the Mini Cooper, we're going to look at our total, and total for our, I'm not going to use t because we already used t. 2, our second state that we're looking at for our momentum, right? So we know that our final momentum, we have a magnitude for it. It's the same as our initial. So I'm going to borrow this as well. So if I take the magnitude of this vector, because we already know the directions are going to be the same, so I take the magnitude of that one, and I have the magnitude of this one. Okay. I'm trying to find the speed. I'm trying to find the magnitude of this vector. So if I have the magnitude of this, that's supposed to equal our m2 times that v2. I'm not going to mark it with an arrow because now we're just looking for the speed, the magnitude. Well, we know the mass in our second state because we were told the cars stuck together. And we said we just add their masses to get that m2. So we just add our 20,000 and our 12,000. Right, and that's going to give us a mass of, I don't feel like rewriting this number, so I'm just going to copy this down, equals our, what's that, 3,200, my bad, times our V2, right? So divide both sides, quick algebra, and we're going to get that the magnitude of our velocity is going to be 10.0971841 meters per second. Right, and remember we check our units. momentum is in kilograms meters per second, and we divide by kilograms, so it's just going to leave us in meters per second. So, and again, we do the same thing. We have our angle and we have our direction. So we have a magnitude and we have a direction, and it's going north of west. So there's west, there's north of it. Here's our 68.2 degrees. So this is our final speed, and here's our final direction. Now we're given a coefficient of kinetic friction between the car's tires and the pavement. And we need to see how far they skid before coming to rest. So we've been talking a lot about momentum today, but now we're going to go back to our old friend, the work energy theorem, right? Because I want to say my initial kinetic energy plus some work done equals my final kinetic energy. That's what we can be thinking about, right? We have some initial energy, we have our initial velocity, so we have our initial kinetic energy. You know, some work is going to be done because at the end, they come to rest. So this is going to be 0. Let's think about what's going to be doing work. Well, we're given a coefficient of friction, so that's a pretty big hint that friction's going to be doing our work for us, right? So really the only other forces acting on the cars during this point is normal and gravity, our normal force from the ground and gravity pulling down, but we're not accelerating into the ground or jumping up off the ground. So really the only work being done is going to be our work from friction, okay? Which is going to be our force from friction, which is our normal force times our mu k. So I was going to say, jumping ahead of myself, mu k, and then our normal force in this case is just going to be our m2g, right? Specifically because we have our mass of both of the cars. So it's our force times our distance. And since we're going, whichever direction we are going, our friction is going to be acting against that in this case. We get a negative work, which I did right before, but we're just going to actually put that in now. But yes, a negative work done by friction, which makes sense because we have energy at the beginning. We have to subtract it so that we can get to our 0 energy state at the end. So what I'm going to do, and also we have to think about what's going in here, because I was putting my M2s and stuff in here, and we said this is 0. Right? This is going to be 1/2 also M2, right? And this is really going to be our V2 here now, which I'm not going to plug in just yet because I don't feel like rewriting that number a few 1,000 times. But, right, because this is, now we're just taking another picture. We said we took a picture before the collision for our initial momentum, and we take a picture after the collision for our final momentum. Now we're using that same picture. We're taking another picture immediately after the collision, but we're taking another picture once it comes to rest after that. So we have really 3 states. We have, right, before our collision, after our collision, and once we come to rest, right? To get from here to here, we use conservation of momentum. And now to get from here to here, we're going to use our work energy theorem, right? So our final state of this one's going to be the same as our initial state for this one. Right, just something we looked at a bit in kinematics, but I just wanted to make sure that we emphasize that here, right? So we can say that minus our mu k m2g times d equals 0. Again, I'm just plugging this in for our work done, and this is our initial kinetic energy. And since, right, there's a m2 in both of these terms, I'm just going to divide that out. So we're left with 1/2 v2 squared. And I'm just going to bump this to the other side because it's negative, equals mu k g d. All right, and we're trying to find out how far they skid before coming to rest. So that's going to be this d here, that distance, because we didn't know that, so we just left it in as a variable. So now let's solve for that because we know our v2, we know mu k, and we know g. So we can solve for d in terms of all of that. Right, so d is going to be v2 squared over, that looks like a z, squared over 2 mu k g. Right, I just divide these two from both sides. And that, plugging in all of our numbers, that's going to give us a distance of 8.6606466019 meters. Right? That's going to be how far the cars slide before they come to a stop. Right? Now we have one more question here. We have a 5 kilogram box on a table with a given coefficient of friction, and we're throwing things at it. We throw a lump of clay and we throw a rubber ball. Right? Both have there's two separate situations. Both have a mass of 500 grams and they both strike with the same speed. Right? But they do different things. The lump of clay sticks to the box while the ball bounces off of the box. So you have to think about what is going to knock the box further, right? So our hint here is that the impulse delivered to the box is equal and opposite to the impulse delivered to the object thrown at it. So let's just make a hypothesis. My educated guess that our impulse, right, which is our change in velocity, has to do with our impulse is our change in momentum, which has to do with our change in velocity. So the rubber ball is going to the right initially, and then it switches and goes to the left. That's a pretty big change in velocity. Our clay is going to the right, and then it's going to the right a little bit slower. That's a smaller change in velocity. So my guess, my hypothesis, and we'll prove it with some math, is that the rubber ball is going to push the box further. Okay? So now we get to do some math and prove this hypothesis. This is the scientific method at work, So we have our mass of the rubber ball plus our V of the rubber ball plus, so this is going to be, I'm setting up our conservation momentum. So we're going to say that our initial momentum of the rubber ball plus the initial momentum of the box, VB1, is going to equal our final of both added together as well. So VR2, that's supposed to be, I'm writing things out of order. MR2 VR2 plus MB2 VB2. Oh, I'm writing things off today. But right, so here's our conservation momentum. We define our system as the ball and the box, and the ball and the box. Right? We do know that our initial momentum of the box, right, our initial velocity of the box is going to be 0, so you can just ignore that. So now, if we want to find how far each object knocks the box, right, we have a coefficient of friction. We're going to do the same thing we did before. We do a conservation of momentum to get us from before the collision to after the collision, and we get a final velocity, and then we can use that velocity in our work energy theorem to get our distance that it traveled, right? So using conservation momentum, we're going to get that our V, right, and our VR and our VB are going to be different, so we get to figure that one out. So solving for not the velocity of the box at the end, because we have the velocity of the ball at the end, so it's going to be VB2 equals, I'm going to subtract and divide, so it's going to be MR1 VR1 minus MR2 VR2 over MB2, which makes sense. Look, this is our initial minus final, right? This gives us our change in momentum of, or it's, if we take the absolute value, usually it's final minus initial, but either way, this gives us our change in momentum of the ball. And the opposite, right, the impulse is equal and opposite to the thing that's delivered. So if it was initial minus final, if we flip it, final minus initial, that's our change in momentum of the rubber ball, which is going to give us our change in momentum for the box. Okay. So now, solving all this out, if we plug in some numbers, punch them into our calculator, we get 3/5, which is 0.6 meters per second. And now we do our 1/2 mb VB2 squared plus our work done by friction equals 1/2 mb, I'm going to call this V3 squared, and then it's still the box. And again, it doesn't matter what I call this because we're looking at when it comes to rest, so that's going to be 0. Our work done by friction is the same as before. We have our mu k times our mg times the distance. Again, it's going negative, it's going opposite our direction of motion. And this mass is going to be, again, the mass of the thing we're looking at, the mass of the ball. the box, sorry, B for ball, B for box. I set it up and it's gotta keep it straight. So same thing I did before, 1/2 M B VB2 minus mu K MBGD equals 0. I can divide out by that mass. I'm gonna say, all right, our D equals, with all of our algebra, VB2 squared minus 2 mu kg, which is gonna give us 0.03669724777 meters. Cool. That's how far the rubber ball is going to knock the box. Now we do the same strategy, but instead of the rubber ball, now we look at the clay. I'm gonna get rid of all the R's and say clay, right? Now we're solving for, again, this final velocity of the box. But now our final velocity of the clay, since it sticks to the box, final velocity of the clay is going to be the same as this final velocity of the box. So I'm going to just simplify this and say VC2 equals VB2. I'm just going to call it V2, some second velocity. So now if I plug this in here and factor it out, now I'm going to solve this equation for this V2. So again, that's how I'm going to be able to get my final displacement of how far the box got bonked, right? So our V2 with all of my algebra, it's going to be MC1 or MC, right? The mass of the thing doesn't change. VC1 over MC plus MB, right? So here's our velocity of the box and the clay together at the end, which is going to equal 2 over 5.5, or if we're simplifying the fraction in a way that matters, 4 over 11, or first of decimal's sake, 0.3636363636 meters per second. So here's our final velocity. Again, that's just our V2. So now we have to do our work energy. Do the same thing we were doing before. But now, instead of having MB here, right, the thing that's moving at this velocity is both the MB plus our MC. Right? The box and the clay are both moving at the velocity, so they're both going to have that kinetic energy, V2 squared. Right? And now our work done by friction, same thing. It's not just the mass of the box. It's going to be the mass of the box plus the mass of the clay. Right? Because both are going to have some gravity, both are going to have some normal force. But the box is the one that's touching the ground, so that's the mu that we're going to be using. Okay? And again, we're ending at rest, so it doesn't matter what that is. So setting this up one more time, MB plus MC times V2 squared minus mu K MB plus MC GD equals 0. Okay. And just as before, wonderful, lo and behold, our masses will cancel out because we can divide those from both terms. And solving for this D, right, we get this exact same expression we did before. Our D is going to be our V2 squared over 2 mu kg. Right? And the magic part about this, it's the same expression, but it is dependent on this second velocity. And we know that this one had a higher velocity than this one, so we know this one's going to move not as far, which is what it comes out to be, 0.013479246 meters. Right? So our sanity check of our velocity is lower, so our distance is lower. It makes sense. It gives us the answer we were expecting, and it's almost like I knew what was going to happen. It's almost like I'm good at physics, but we proved our original hypothesis up here, right? He said the rubber ball would push it further because it had a greater change in momentum and had a greater impulse that would then be delivered to the box. And we were right. Our rubber ball pushed it further. right? All right, well, I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this recitation or any other problems that you want me to try to explain, and I'll do my best to try to explain them because I guess Sydney explains stuff.